Hello. So today I'm going to talk about atomic emission spectroscopy, Light Me Up, discovering the history of light, black body emitters, and the quantized nature of electronic energy. So to begin with an introduction, how is the speed of light measured, and how is the electronic energy level of molecules and atoms quantized? So there's many classical concepts like the wave particle duality, and when Max Planck introduced the quantization of energy, we hypothesized that black body is not continuous, and hydrogen and deuterium will have isotopic influence on the line spectrum. Black body should not be continuous because I think it should be a quantized energy and is affected by temperature at extreme high and low temperature limits. The black body's orbits may deviate from classical predictions and change the emission spectrum. And the line spectrum will have isotopic influence from hydrogen and deuterium. There should be a shift in intensity variations with the line spectrum from the hydrogen and this isotope deuterium. So to begin with part one of the experiment, we have the speed of light measurements. The theory behind is starting with um, fundamental concepts like Maxwell's equations, which introduced the existence of electromagnetic waves and show that these waves propagate at a constant speed. And all of this led to the understanding of the speed of light we have today, which in this simple equation, we have an equation with speed of time. The methods we use an instrument called the oscilloscope. It was used to measure a pulse of light reflecting off the mirror. The pulse of light travels across the distance to reflect off the mirror and back to the starting position, and where the pulse is detected again. And only now will be delayed with the time compared to the outgoing light pulse. And the speed of light is measured by measuring the time difference between two peaks and the distance that the light traveled. And there's 5 measurements taken. So jumping into the results, table 1.1 is the speed of light data with the 5 trials. And since the speed of light is first reflecting off of the mirror, so it's 1/2 of the speed of light. So multiplying that by 2 gives us the speed of light. And table 1.2 gives us the experimentally determined speed of light with the mean speed of the 5 trials and the standard deviation. As we can see here, at the distance of 4.57 meters gave us the best results. And accurate distance measurements and optimizing the optical setup would improve the results. The variation between the speed calculated at low is low because it had standard deviation has a magnitude of 10 to the 6 compared to the large number of the speed of light at 10, magnitude of 10 to the 8. It means the data are close to the mean. So here's the spectrum and the 2 peaks of detection, where the peaks are the signals coming back into the detector, and the difference in peaks is the time difference in nanoseconds right here. So moving on to part 2 was the black body emission. The theory behind is Rayleigh and Jean's black body radiation equation developed in the early days, and where dp over d lambda is the intensity is equal to equation 2 right here, where k is the Boltzmann constant. And Max Planck came along and used Rayleigh-Jean's equation and then introduced a new concept, which I previously mentioned, is the quantization of energy, where the Planck intensity can be calculated by equation 3 right here, where h is the Planck constant and k is still the Boltzmann constant. And we also adjusted the Planck intensity to make sure the intensity values of the Planck calculated intensity match closely to the Planck intensity values. So that will be shown in the data here. I will jump to later. So it's done by multiplying the Planck intensity values calculated by a ratio of the measured spectral intensity at a given wavelength by the Planck intensity at the same wavelength. The Ribber constant works only for hydrogen isotopes because it is an empirical formula that is based on the Bohr model of the hydrogen atom, can only be applied to hydrogenic. So the methods we used was a simple ocean optic spectrometer with the fiber optic cable and lens attached to the entrance port. And it was positioned in front of the light source, making sure not to saturate the detector. And the bulbs we use, light bulbs we use were the incandescent, fluorescent, the LED, and also the sun and lamps. So jumping into the data we got, table 2.1 shows the maximum wavelength of absorption for each black body emitter. As you can see, for the 3 light bulbs, the wavelength was fairly similar at around 600 nanometers, and for the sun is very lower at 500 nanometers. And table 2.2 show the Planck and Wien temperatures of each black body emitter calculated. So the Planck and Wien temperatures agreed pretty well, with the difference around 20 to 70 kelvins for each of the 3 light bulbs. And the Planck temperature is found by repeated trial and error by changing the T in the Excel calculation and fitting the curve to the graph. As we can see here, LED was the hottest in wine temperature, and the incandescent followed the Planck equation the best shape. So here's the Grafton spectra. This is light bulb one of the incandescent. As you can see, it followed the Planck fitting fairly well as compared to fluorescent and LED spectrums. And the last one is the sun's blackbody radiation. So moving on to the line spectrum emission of hydrogen in this case. The theory behind is that the spectrum emission involves the quantization of energy once again, and transition between the levels and an emission of photons with discrete energies. And the quantized energy levels, according to quantum mechanics, is electrons and atoms and molecules can only occupy certain discrete energy levels. So with the Bohr model that explains the line spectrum of hydrogen and the wave-particle duality, electrons exhibit both particle and wave-like properties. Rydberg, the Swedish scientist, found that for hydrogen, the emission line could be calculated by equation 4 right here, which is 1 over lambda equals the Rydberg constant, and n here it's the electronic energy level as 1, 2, or 3, and RH is the empirically determined Rydberg's constant. And Niels Bohr came along and used the Rydberg's constant and developed the equation 5 right here that can be used to determine the Rydberg's constant, where E represents the elementary charge, epsilon naught is the vacuum permittivity of free space, H is the Planck's constant, and C is the speed of light. And also mu is the reduced mass given by equation 6. The ratio of Rydberg's constant can be calculated if we separate the reduced mass from Bohr's equation, which is given in equation 7. And the last one is just the energy of the photon. So the method we used was a photomultiplier tube and a discharge lamp, where a photomultiplier tube was a light detector that amplifies incoming photons into electrical signals, widely used in low-light applications like spectroscopy and fluorescence detection. Discharge lamp source powered by passing electric current through a gas or vapor, in this case, which was hydrogen, is utilized for its efficiency and ability to produce specific wavelengths. So the photomultiplier tube and discharge lamp both require high voltage, so care needs to be taken when operating. Monochromator was used to disperse the light emitted by the discharge lamp. The monochromator is simple. It consists of an entrance slit, a grating to disperse light, and an exit slit. So the hydrogen discharge lamp was set up to optimize the signal. Signal optimization was done using the PMT and adjusting the voltage in line with the resolution, but adjusting the slit of the monochromator. And that is done by holding the monochromator at a hydrogen emission line of about 4,101 angstroms, while adjusting the optics to minimize the optical setup and maximizing the signal. So moving on to the data we obtained, as we can see, table 3.1 and 3.2 here are the energy level transition peak positions in wavelengths and relative intensities and energies for both hydrogen and its isotope deuterium respectively. So as we can observe here, the intensity of the hydrogen and deuterium decreases at shorter wavelengths down here as seen. So that is because there's less population at higher energetic levels. The intensity of a spectral line depends on the transition probability, the population of the initial and final states. And theoretically, the ratio of the signal intensity could be calculated with the Schrodinger's equation for hydrogen, and the Rydberg's constant could be used. So moving on here to the second page of tables, table 3.3 and 3.4 were the experimental and theoretically determined Rydberg's constants respectively. The experimentally determined constants were plotted on a fitting and got determined from the slope, and it was 1 over lambda versus 1 over n squared, where n is the electronic energy level. And the theoretical determined Rydberg's constant used equation 5 of Bohr's Rydberg's constants equation. And as we can see in table 3.5, the percent error is not much, and so there's good consistency right there. So moving on to the graphs and spectrums, the emission line obtained in this experiment was broadened and not as sharp and narrow as they would be in theory. As we can see here, the focused and zoomed in lines of each peak. So that is the broadening. Natural broadening is related to the Heisenberg's uncertainty principle. There's an inherent uncertainty leading to the natural line broadening. The shorter the lifetime of the excited state, the broader the spectral line. And other external conditions like the collisions of other atoms During a collision, the energy levels of the atoms affects the emitted or absorbed radiation, and also other conditions like nearby electric fields, the temperature, the pressure of the room. So moving on, these are the zoomed-in spectrums for each peak for 62, 72, 82 transitions, and finally n equals 92 transitions. As we can see, hydrogen is the taller peak and deuterium is the shorter peak following right next to it. And here are the slope fittings used to determine the hydrogen Rydberg's constant and the deuterium Rydberg's constant. The slope here will determine to be the experimentally determined Rydberg's constants. So in conclusion here, we have the measured speed of light, the Planck and Wang temperature were calculated and experimentally determined the Rydberg's constant. The hypothesis that black body is not continuous, there is a typo here, it is rejected because black body radiation is continuous. It exhibits a continuous spectrum, meaning that it emits radiation at all wavelengths. That is in contrast with the discrete quantized nature of certain other types of radiation, such as the line spectrum of gases. And the intensity depends on temperature only because that is according to Wein's law. And the emission of radiation from a black body is the statistical mechanics. The thermal excitation and density both help bridge the gap between discrete energy levels to make a continuous spectrum at the macroscopic scale. And some limitation of our method is that it is limited to hydrogen. The hydrogen emission line are specific to hydrogen atoms. They don't have information for other elements. And their sensitivity, like I previously mentioned, the natural line broadening and the temperature and pressure affecting it. And alternative methods include absorption spectroscopy. It's using the emitted light. The absorption spectroscopy involves analyzing the light that passes through a sample by examining the absorption lines in the spectrum, the energy level that transitions of hydrogen atoms can be calculated. The absorption spectroscopy is often used in combination with emission spectroscopy for more comprehensive analysis. So other methods include microwave spectroscopy and laser spectroscopy. So overall, the experiment was performed consistently while agreeing Planck temperature and Wien temperature. And the speed of light is close to the widely accepted value of the speed of light, where the standard deviation is close to the mean. And there is low error for the Rydberg's constants for both experimentally and theoretically. Thank you very much.